All right, after some technical difficulties, I'm back at this. I left off on number 26. We were looking at if light was coming through these and then they created a bright spot and then a dark spot. So let's say that these had the same intensities. Let's say they both had intensity. I'll just make up a number of 2 and 2. So if they both have 2 and 2, then at the bright spot where they're coming together, working together for, let's say that's the amplitudes, they'd come together and they'd have an amplitude of 4. And where it was a dark spot, it would be a 0 because they exactly cancel each other when one of them is out of phase at the destructive interference spot, as they're saying here. But now if we make this dimmer, and this one only has an amplitude of 1, where this still has an amplitude of 2 here, then at the bright spot, they'll add together to only be a 3. And at the dark spot, the 1 can't cancel the 2, so there'll still be a 1 left over. So the dark spot actually gets brighter as the bright spot gets dimmer, going from 4 down to 3 and from 0 up to 1. So that's why the right answer is C on number 26. Let's take a look at this first one here. Well, we just have a 5% for the R, and since R is squared, we end up needing an uncertainty of 2 times 5% or 10%. So that little topic 1 question is in here. For 18 here, we see that we have a fast and a slow area. And in the cold air where it's slow, we know that the wavelengths will be close to each other, and then it's going to speed up, move away from the normal line, and it'll be along this line here. So 3 is the correct answer for C. I guess it could have internally reflected. If they had one in here, we'd be wondering, like maybe that could happen, but it wouldn't ever come straight back at us like that. That would be incorrect. So that's interesting. Continuing on here, we have the speed of sound is C, and when you have Doppler effect, I think we all understand that that doesn't change the speed of the sound, so it's still C. We had an earlier one in the previous video where we saw that. If we look at this one, we can see that the waves in front of it are getting bunched closer to each other, and these ones are farther apart. But the sound wave itself is still going the same speed to the right here as this one's going to the left there. It doesn't change the wave speed. It changes the observed frequency because these are closer to each other as they hit the observer. So we don't expect an actual change in the speed. It's just A here for 19. All right. Sweet. Let's look at this one. We have a standing wave. You can see I already did this and had some technical problems. So here we go. We have a standing wave. We have 2 nodes because it's 2 successive nodes. And in between the node, this string is going up and down and up and down and up and down. Isn't that nice? And so here it is at one point, then later it's in the middle, then later it's at the bottom, then it comes back to the middle, and then it's at the top again. And so any particular one is just moving back and forth like this. And they're all moving together in phase because the string goes up, all of them go up. String goes down, they all go down. So they're all moving in phase, so they all have the same frequency. And this is for standing wave only. They're not going to have the same amplitudes. This one where they're closer to the antinode is going to move a lot farther. And the one here that's real close to the node is hardly going to move at all. And there'll be no energy at the nodes and lots of energy at the antinodes. So B is the right answer for that guy. And let's take a look at the next one. So with the next one, we have 2 waves going through each other. And as they go through each other, they're uninterrupted. They don't affect each other at all. So the shape of this one after it's gone by will still be the exact same shape. This one, as it goes by, won't change shape. So B will be the right answer for 21 there. And for 22, let's see what we get. We need coherence. Coherence means that they're in phase, or at least they have a same constant phase difference. And that's the necessary condition, is that at least they have the same phase difference if they are going to be vibrating such that they make a pattern. And I've talked about that before, and I've mentioned that if these 2 things are exactly in phase, you'll get the pattern according to the reaction. But if they're out of phase, you get these weird shapes, but you still get shapes that are happening as long as they are consistently with the same phase difference. You will still see a pattern. So that's the necessary condition. Strangely worded question, but we're going with it. Let's see what we got next. So after 22, go to 23. And it looks like D is the right answer. Let's see if I can remember what's going on here. Double slit experiment. Oh yeah, we had the wavelength and we had 3 fringes. And then if the wavelength is half as big, then we're going to have half as many. And you can look at the equations from topic 4 to see that. Or you can just get the idea because everything about the pattern gets tighter, mixed, they're closer to each other. It'll be easier for the phase to work out in terms of the change in path length being smaller in order to create more fringes. So you'll get twice as many fringes, and you had 3 fringes, so that's why you end up at 6 fringes. So excellent for that one. Now we're up to 24. And let's see what's happening here. Looks like these two are two identical sources in a ripple tank generate a wavelength of lambda. The interfering waves produce the wave pattern seen below. Which of the label lines is a path difference between the phase equal to 1/2 of wavelength? So this is delta L, and we know that straight on, which is here, where I would have called this n equals 0, where we have a bright spot, and then this is our first dark spot, so this is half of a wavelength off. This is 1 exact wavelength off, so this would be 1.5 wavelengths off at 3. So we expect the answer to be C there on number 24. All right, there we go. The relationship between 2 measured quantities P and Q is of this form, so it's an exponential relationship where K and N are constants. If you plot log P, let's see, what are we going to get to understand? So if we do log of both sides, we get log P equals log of K Q to the N power. We know our log rules, so we know that when you have multiplication, it becomes addition. So now we get log P equals log, I'm going to change the order here, and we get Q to the N power plus log K. Finally, this exponent will fly out in front, so we get log P equals N log Q plus log K, and these could be LNs, this could be any kind of logarithm. So this is my Y. My M is N, it's the power, so that power becomes a slope. This is a very important Y equals MX. We're graphing log Q on X and log P on Y. And then log K is going to give us our Y-intercept. So now we're ready for the question. If you plot log P against log Q, so that's what we've done, log P is on the Y and log Q is on the X, will enable us to get the value of K to be determined using the Y-intercept, because this is Y equals MX plus B. So the Y-intercept is what we're after for this one. So there you go. It would be A. Excellent. 21, back for standing waves again. Lots of topic 4 in this, because this old test is from a year when multiple choice was more about topic 4, because the option had the more topic 9 type questions. But good review of topic 4 on these multiple choices. We're up to 21, and we have the transfer of energy in a standing wave is obviously going to be none. And then we have the amplitude of vibrations of the standing wave. We know we have variable amplitude. We know that. I just talked about that when we did this example here. If you recall, as you move along, this amplitude is going to be tiny, where this amplitude is going to be big. So clearly, B ends up being the answer here on 21. Okay, I'm running out of time, so I might speed up just a little bit. 2 pipes, P and Q, are the same length. P is closed at one end, so P is closed at one end, and Q is open at both ends. Okay. The first fundamental in the closed pipe is 220 hertz. And this wavelength is going to be shorter, so it's going to go up to 440 hertz. I know that because the wavelength here is shorter, so the velocity is the same. And we have velocity equals frequency times, velocity equals frequency times wavelength. So the same velocity, so if the wavelength gets shorter, which it is here, then the frequency has to get bigger up to 440. So that's why we get B, because we have half the wavelength. Remember, this one is closed open fundamental, and then this one does this where it's two times more wave inside the pipe here. So this is 4 times L equals the wavelength, and then this one is 2 times L equals the wavelength. So the wavelength is shorter, thus the frequency is higher. I did that in class before we started having these e-learning experiences. Where are we at? We're at 23. And 23, we're going to have the sounds of two sources interfere. The resulting sound has a frequency of 4, and we just have to add or subtract 4 from 252. So we're going to get, let's see, beat frequency of 4, the frequency of the sources, thus have to be 4 apart and an average of 252. So it looks like A works. Anyway, beat frequency isn't in there anymore, but it's kind of nice to know a little bit about it. Remember, this is when you had one wave, almost the same as the other. So they might have started out in phase, but eventually go in and out of phase because their wavelengths are slightly different. So they work together sometimes, and then they end up fighting each other sometimes. I didn't do a very good job of making this wavelength be smaller. So they end up fighting at other places, even though they were together for a while. And that's called a beat frequency. 24, I like either B or D. They have to have the same wavelength, and they need to be coherent. It's interesting for them, they said B was more important, and that's the way they're defining coherent, that they don't necessarily have to be perfectly in phase. This is 2005, so the verbiage has changed a little bit. In any case, we're almost done here. We got our last one. Number 25, we have 2 loudspeakers. Each of the loudspeakers is continuous sound at the same frequency, so the same wavelengths are occurring. A microphone is moved along P to Q, so it'll be loud and then quiet and loud and then quiet as it moves through. So which one of the following actions on its own will lead to an increase in the distance between the maximums? So these fringes need to get between loud and then the next loud, because going loud, quiet, we're wanting that to get bigger. And so obviously decreasing the frequency of the sound will do that, because that's making the wavelength longer, because it's going lower, so that's a longer wavelength. Okay, so there we go. Decreasing, so that's for frequency, so we know A had to be right. Increasing the separation actually makes the fringes get closer, so C can't be correct. And the distance, if you bring this closer, then these fringes all get smaller because the angle stays the same. So that's why we had to have A. And that's the end of the multiple choice. I'm exhausted. I hope it helped you a little bit, and I'll try to get this posted today. So good luck on your test coming up on 4 and 9. Again, this ended up being more 4 review than 9 review, but hopefully it helps you out.